So today I'm going to talk about frame of references and then I will talk about the Galilean transformations. So consider a train moving at a constant speed, right? Then if I look at the fellow passengers which are close to me inside the train, if I am sitting inside the train and the fellow passenger is also, then that fellow passenger seems to be stationary for me. But if I'm on the platform and looking at the passengers inside the train, then those those passengers inside the train seems to be moving for me. So that means there are different frame of references, and say when I'm on the platform, then if I'm observing something when I'm standing on the platform, then it is a stationary frame. But when I am inside train looking outside and train is moving inside a train and train is moving, then I am observing, or I am in the moving frame of reference. So that means on the basis of the rest and the motion, means when I am observing something, when I am at rest, then that is known as the frame of reference, frame of reference. Then that is known as rest frame of reference. And when I am moving, I am inside a moving, say I am inside a moving train, and when I am looking around, then that means I am in the moving frame of reference. I am looking at the objects when I am moving, right? So that is known as moving frame of reference. So that means on the basis of the rest and the motion, I can classify frame of references as rest frame of reference and the moving frame of reference. But if the object is moving with the, or if that moving frame of reference is moving with a constant velocity, constant or uniform velocity, there are two possibilities. And another is that if it is moving with the non-uniform velocity, non-uniform velocity means the velocity is changing, v is changing, then this is known as this frame of reference. And these are the two different type of classifications. This is known as inertial frame of reference, and this is known as non-inertial frame of reference. Inertial frame of reference. So, and what is a frame of reference? Let me talk about it now. A frame of reference set of coordinates used to describe the position and the motion of objects, right? And then types of frame of references, I talked about earlier that there are two types of frame of references: inertial frame of reference and the non-inertial frame of reference. Here velocity is changing, that means the frame of reference is accelerating. And here the velocity is uniform, that means Newton's laws of motion will holds in the inertial frame, right? Now there is a need that how laws of physics, because there is a need to relate the laws of physics when they are observed from the one frame of reference and these laws are observed from the another frame of reference, that is a non-inertial frame of reference. So there is a correlation between the laws when they are observed in the one frame of reference and they are observed in the second frame of reference. So for that, then Galileo Galilei in 17th century tried to relate the motion in the two frame of references, or the try to relate the laws in the two frame of references, and the transfer, and he used certain transformation. These transformations are known as the Galilean transformations. Means they relates the coordinates of an object in two different inertial frame of references moving at constant velocity with each other, right? So if we consider two frame of references, one is the stationary frame and another is the frame S prime, which is moving with the constant velocity b, it is related to S, and these are the transformation equations. I will prove it later on. And even because if the moving frame of reference, say this is one frame and this is another frame, say it is S frame and it is S prime frame, and say object will be somewhere here, and when I try to look at this, its position vector will be this and its position vector will be this when it is seen from S prime frame. Then, and S prime frame is moving with the velocity v along this direction, so it travels a distance vt. So how this x prime is related to x? So it is simply x prime is equal to x minus bt, but along y axis there is no change, so y prime is equal to y and z prime is equal to z. So these are collectively known as the Galilean transformations. And here time will not change, because I will talk about this right now, that what is the meaning of Galilean transformation. Let me draw a coordinate system. And say there is a coordinate system, let us call it as a x, it is y, and it is z. Say it is like this, and initially, and there is another frame of reference, let us call it as a x prime and it as a y prime and the z prime. Initially both the frame of references are intact, right? Suppose there is a lighthouse, there is one ship at this point, and there are two persons near the ship who are observing this lighthouse. But what will happen? Say one person is remain in the seashore and another person starts moving in the ship along towards this seashore. What will happen? A person who is on the seashore, he is observing the lighthouse, and for this person lighthouse will remain as it is. But when a person who is inside the ship and the ship starts moving towards the lighthouse, say it is lighthouse, so if this starts moving towards the lighthouse, what will happen? Lighthouse seems to be moving for this person, right? So what will happen, that how the distance of the lighthouse related to the in the two frame of references. So for that, let us try to draw a diagram. Say this is a point P, it may be any point, and say this point is and I am observing this point P, and the P is represented by x, y, z, and say for the person who is at this point, the time, the clock gives a t time for this, and initially what will happen, this frame of reference is also here, it is overlined, but with the passage of time this stationary frame will remain as it is, but this frame starts moving towards this direction. It starts moving this direction. this frame of reference. It is moving in this way. And say initially the time for this clock is t, and say for this clock the time is the t prime. But as we know that when with the passage of time, say, or in other words I can say that initially both the clocks at the initially here, what will happen, say initial time for this clock is t and for this clock is t prime, initial time. So what will happen in capital T time, this moves this distance. So that means after t time, capital T time, this clock reads t plus capital T, and similarly this clock reads t plus capital T. Means this t will not change. This is their initial time. And if I suppose assume that initially t is 0 and its t prime is also 0, then both clocks takes the same time. That means the time t which I am considering here, it is independent of motion of frame of reference. So rather than taking capital D, I will take this, say this time is t and this time is t prime, and both the times will remain the same. So that means t is equal to t prime. Why? Because this is independent of motion of frame. Right? So now let me try to so that means the t time is for this and the t prime for this. So when I try to look at the particle from this frame of reference, this point P is represented by x prime, y prime, z prime and t prime, right? So now what will happen? When I try to look at this particle, let me see what is x and what is y. So when I try to look at this particle, so what is x and the y? See, since it is frame of reference is only moving along x-axis with the v velocity, means s prime frame is moving along x-axis with the v velocity, right? So that means y and z will not change. So in t time, say in t or t prime time, it travels this distance from this point to this point. And what is x? In this frame of reference, because the coordinate is this one, so this distance is x, which I am representing like this, and this distance is x prime. So if I try to look at this from simple geometry, what I am getting, that this x, this whole distance is equal to this distance plus this distance. So this comes out to be x prime plus vt. So I can write down x prime is equal to x minus vt. So what is it? It is the Galilean transformation. That how position of a particle related to the frame of reference in the another frame of reference, means it is the position of the particle when it is seen from the moving frame of reference. It is related with the frame of reference which is stationary. Also y prime is a y and z prime is equal to z and t prime is equal to t. So these are known as the Lorentz transformation. And I can do reverse also. Oh, not v, but it is a plus, sorry. Yeah, it's fine. Yeah, So I can write down either this way or this way. So prime means moving frame. S prime means it's a moving frame. That's what we have to remember. Or you can write down S naught for the rest frame, or you can call it as well SV or S prime for the moving frame. Whatever you want to do. So this is one case which I am considering, that the frame of reference is again moving along the one axis. But if frame of reference is moving in a plane or in a space, then what will happen? So for example, let us try to again draw a diagram. It's like this. So say this is x-axis, this is y-axis, and say this is z-axis, and say this frame of reference is moving along this direction with a velocity v, and initially both the frame of reference is at the same point and it will travel at this distance in the vt, and say this is x prime frame and it is y prime frame and it is the z prime frame. The particle will be somewhere here. When the particle is seen from this point, it was like this, and when it is seen from this frame of reference, it is like this. So how? Say it is the position vector in the moving frame of reference. Let us call it as a r prime, and say it is a r vector. So how is r vector is related to r vector? So let me recall, as I know that x is equal to x prime is equal to x minus bt, as I did earlier. So what is happening? Say this frame of reference is moving with a constant velocity in the space. So what will happen? This velocity vector is basically, it has three components, vxi cap, vyj cap, and plus vzk cap. So that means it is moving with velocity vx along x-axis, and it is moving with velocity vy along y-axis, and it is moving along z-axis with the z direction. So that means in the similar fashion, rather than writing y, I can write down y prime is equal to y minus vt, but not v here, vx and the vy, because these are the different components, right? And similarly, z prime can be written as z minus vzt. So therefore, this r vector is equal to xi cap, yj cap, zk cap, and similarly r prime vector can be written as x prime I cap plus y prime j cap and plus z prime k cap. The interesting thing is that since x-axis and x prime axis both are parallel, and y and the y prime both are parallel, and z and the z prime are also parallel, so that means I cap, j cap and k cap will remain the same for both the frame of references. They will not change in S and the S prime frame. Oh wow, that means what? That means I can write down this r prime frame is equal to x prime I cap, y prime j cap, z prime k cap. So I can write it down as x minus bxt I cap it is y minus vyt j cap plus z minus vzt k cap. So it can be written as x I cap, y j cap and the z k cap minus vx plus vy, it is I cap, it is j cap and vz k cap, and t will remain as it is. So it is r vector minus v vector t. So this is the Lorentz transformation when moving frame of reference is moving in a space. There are different cases also, we can do those cases. Say something is moving along a frame of reference is moving along a y-axis, then what will happen? Say this is one frame of reference, say it is x-axis, it is x-axis, it is y-axis, and it is z-axis. So if frame of reference is moving along this direction, then what will happen? Because this is x-axis, this is y-axis and z-axis, but with the primed frame. So one is the S frame and this is S prime frame. So then what will happen? I can simply write down it as a x prime is equal to x and the y prime is equal to y minus bt, because it is moving with the velocity b along this direction. And z prime is equal to z and t prime is equal to t. And when something is moving in xy plane, because that is not changing. When something is moving in xy plane with the velocity v, then what will happen? X prime can be written as x minus vxt, y prime can be written as y minus vyt, and vz is equal to 0, because z will remain the same. Then z prime can be written as z and t prime can be written as t, right? So this is a brief overview of the Lorentz transformation which I discussed here. So 17th century Galileo Galilei developed the concept of Galilean transformation, because Galileans' interest in the nature of motion, that investigation of objects' motion in a different frame of reference. You say when I am looking from the earth, just a certain body, or when I am moving in a ship, or right, or in a bus, or in a car, right, and it laid the foundation of the classical mechanics. At that time, ships there and boats are there. So when I try to look at something, then how things are related numerically to each other, and it laid the foundation of the classical mechanics. It also laid the principle of relativity, right? And if I remember my earlier days when I'm a school going children, then when I run, I saw at the moon, and moon is running behind me. So how that will happen? When I stops, moon stops. So that means these things will fascinate us, and these Galilean transformation will help us to understand such type of motions. Significance, what are the significance of these? Galilean transformation, mathematical expression for the principles of relativity, which states that laws of physics are same in all the frame of reference. Means it never happens that if certain law of physics is valid in the when I am stationary, and when I starts moving, laws will change. If that will happen, we need to modify the law. But in other words, I can say that physics law should remain same in all the frame of references, means inertial frame of references, because the frame of reference is moving with the constant velocity, and it forms the basis of classical mechanics, allowing us to analyze the motion of objects in the different frames. What are the limitations? They work very well for everyday speed, but when something is moving with a very high speed, means speed which is equivalent to c, it's near about that, then these transformations will not work. I will talk about it later on, and how will they break down at the very high speeds approaching the speed of light. In such cases, we need a more complex Lorentz transformation, which are originating from the spatial theory of relativity, right? So I think This is a brief conclusion about this, and thanks for watching this lecture. And I will in the next lecture I will talk about the invariance of various physical laws. Say mass is invariant, time is invariant, length is invariant, and then I will talk about that acceleration is invariant quantity. But interestingly, that the velocity will not remain invariant quantity. Then I will talk about how Newton's laws are invariant under Galilean transformation. Then law of conservation of momentum and energy. All I will talk about. This is a very interesting lecture. Next lecture, that how we mathematically look at all these things. So that's all for this lecture.